Welcome to this another important session on transducers. Today we look into the programmable logic controller. It's what we mean by this PLC, what is the necessity or need of this PLC, its general structure, it's a simple operation where it could be used in which kind of applications, it finds its role, and with the help of relays and registers, which its important components that PLC is going to operate. So basically, what we mean by PLC, it is nothing but a solid state digital and industrial device. You can see here this device specifically we are calling it as an industrial device. So widely used and accepted device as far as the data acquisition is concerned universally compared to other devices. We have got amplifier or rectifiers or oscillators, many things are there. But among all those things, we have seen DFM, DTM, we have seen inverters, everything. But this one you can see it is accepted as industrial device, very important device. So its importance lies with its name itself, programmable logic control. It is going to, wherever control is required, it is used normally. So common thing it became. So it is a solid state made up of a silicon or germanium, any kind of a silicon material like our rectifier diode or transistor, anything like that, SCR. And it is a digital. So PLC or programmable logic controller is a solid state, digital and industrial device. So how we can explain? It is made up of any kind of a silicon material and widely find its application as its digital role. Like the name itself will indicate, we can simply program it, what inputs it has to focus and what outputs it has to control, and widely accepted as industrial device wherever controlling is required. So its a precise definition will goes like this. So according to NEMA, National Electrical Manufacturer Association. So its a precise definition, it will go like this. So PLC can be defined as a digitally operated electronic system. So each word is important here if you are going to write its definition. It is defined as a digitally operated electronic system. Digitally means either we have the user interface here, we'll be operating it with some user kind of interface or GUI kind of interface digitally, either zeros or ones or some user friendly notations. So digitally operated electronic system designed for use in industrial environment. This is very important. Specifically, it is designed suited for the use in industrial environment. So very harsh environments will be there, which uses programmable memory. So programming, if you are doing means we need to have some memory there, which uses programmable memory for internal storage. Okay, for internal storage of whatever instructions you are giving, or it will be processed to provide you the further processed outputs. For user oriented instructions, for user oriented instructions, for implementing logical sequencing, timing, counting arithmetic to control the various operations. So this is the complete and precise definition for the PLC as given by National Electrical Manufacturer Association. So PLC can be defined as sorry, a digitally operated electronic system designed for use in industrial environment, which uses programmable memory for internal storage for user oriented instructions. We are going to store instructions there. For which purpose we are using instructions? For implementing logical sequencing, timing or counting arithmetic to control some operations. So through digital or analog IOs, inputs or outputs, many types of machines and processes can be easily controlled or adapting this PLC. So this is what we mean by PLC. So in short, in one sentence or some few words, we can tell. So PLC is something like a widely accepted controlling mechanism which is made up of solid state devices or elements. So why this PLC? So why it is so much accepted universally? So one example, with the help of example, we try to understand here. So when the switch turns on, assume that it's required. So all of you listen here carefully. So this is the example. With the help of that, we are going to realize the importance of PLC. We'll have here one switch, and it is with the help of that we are going to turn on the solenoid. Solenoid, it is something like electromagnet. So that is going to provide uh, the flow of charges without any communication. So assume that it's required to turn on solenoid for 10 seconds. Then turn it off irrespective of how long the switch is on. Means we do have one switch. I'll just simply turn it on. But with the turning on of the switch, our solenoid will turn on. But I will not turn off the switch manually. After 10 seconds, solenoid will automatically should have to turn off. I will turn on the solenoid only once with the help of the switch. After 10 seconds, I want my solenoid to turn off automatically. So this can be done by an external timer. We need to have some timer or a counter. So that will count for 10 seconds equivalently, and automatically it will send a signal to turn off or it is going to turn off directly the solenoid. So the problem will come like this. What if the process involves more than 10 solenoids and 10 more external timers are required in that case? Isn't it? If you have only one solenoid, one timer is sufficient. If you have 10 solenoids, then you need to have 10 separate external timers. If you have 100 or 1000, that is practically not reliable one. So many timers to have dedicated timers. So the hardware much costs. So and if the processors also require to count how many times switches individually to turn on. Okay. So what is our starting problem? The starting problem is, so you have only one switch and you are going to turn on the solenoid. Okay. If you have more than one or more number of solenoids, then you will get the problem of having dedicated timers that will incur more hardware cost. Along with that, this system, now the problem is only one thing. You turn on the switch, solenoid will be turned on only for 10 seconds, then it will be turned off automatically. Along with that, suppose if you also want the process to count how many times you are going to turn on each solenoid or timer. So for that we need dedicated counters also. This would again requires many external counters. You can see 10 timers, 10 counters, 100 timers, 100 counters, like that. Hence, the problem will become more and more complex if your requirements for the process or application will go on increasing. So where this PLC will come into picture. So with help of PLC, simply you program to count its inputs and turn the solenoids on at particular timings. That's all. Not all hardware timers and hardware counters are required as a part of PLC. Only few hardware timers and counters are sufficient. Remaining software timers and counters can be made with help of coding or programming. So with the help of that only we are going to be able to control many number of solenoids like this. So PLC knows what to do through program. that is developed and entered into its memory. PLC knows that what to do through program that is developed and entered into its memory. Okay, so means we have to feed what inputs it has to uh, operate and what outputs it has to provide. That's all. With help of program, it can automatically process all the things. So let us see after observing its definition and the structure, sorry, the necessity of the PLC. Next we'll go brief about the general structure of the PLC. So if you look at this one, normally it consists of these blocks here. Input circuitry, central processing unit, memory, output circuitry. Means you have the CPU, dedicated CPU will be there along with its dedicated memory and IO circuits. Now this one is going to interact with the real world with the help of this block, these many blocks. So it contains counters as already discussed. It is having some hardware and many software counters which are actually required in the previous problem just we have discussed. Timers, some hardware and many number of timers will be there. Output relays means relays nothing but high power switches which are able to connect to the outputs after when our data is processed, then we want it to be uh, outputted or displayed on the display. So in that case, output relays will be required. So that can be controlled with the help of PLC. This is coming under the part of the structure of PLC itself. So data storage is required separately for the dedicated data storage for the PLC in order to store these instructions, its operating parameters, intermediate results, and processed results, and its various inputs and outputs. Input relays will be there. So input relays will come into picture when we are going to accept the inputs from the real world. Okay, you are suppose if you want to measure temperature, if you want to measure humidity, if you want to measure water level, if you want to measure uh, pressure, force, like that. So for each of these things, we need to have separate dedicated relays which are automatically controlled with the help of the PLC. Internal utility relays which are actually used here. Hello, yes. Internal utility relays which are internally used for some various intermediate operations. So like that, it has got 6 other blocks as a main part of this PLC. Now let us see what I mean by the basic relay as far as the PLC is concerned. That is known as a PLC relay. If you look at this one, we have the DC battery here. 2 coils are there here, top one and bottom one. So below one, it is a DC energized by the DC source with the switch, and relay is there in the form of the coil that is closed now. And now it is coupled with the top loop here. So it is having AC source and the bell will be there. Okay, AC source and bell will be there having some contact. Okay, so AC source and bell will be there having some contact that is open. So that is a AC relay. Okay. So DC, it is energized by the DC lower loop. That's what is a DC relay, and above one is the AC loop that is energized by the AC source. So what we are doing with this, the square box, what he is indicating here, it has a contact. So this coil in the DC that is closed here, that has been used to control the on and off of this switch in the upper loop. That is AC relay. So when you close it, then only you will get the bell ringing. Means we are trying to, with the help of this DC switch, we are trying to on and off of this bell, which is actually energized by the AC. This is the basic relay what we got understood by the PLC relay. So we can see here hybrid one, we are going to turn on and off of the bell with the help of the DC switch, which is actually analyzed by the AC. Understanding? This is a very key element. Next one, we'll try to understand various varied applications of the PLC with the help of the ladder diagram with the various symbols. Okay. So now you can see here. So this is the symbol which is used as the contact of the relay. Okay. So two parallel plates vertically, which are close to each other, are used to represent the contact of the relay. So this one is the circular symbol is used to indicate the bell used as a coil of the relay. So coil of the relay is indicated by the circle and the contact is indicated by the two parallel plates. So PLC knows and cares about which output it has to turn on. We have to feed that one with the help of the programming coding using these symbols or whatever. That we'll see very soon. PLC also knows where everything is located, like all devices with some addresses. Like whatever, because if you look at this one, no, the actual structure, PLC knows where input relays are located, counters are located, timers are located, timer 1, timer 2 is located, timer 10 is located, internal utility relay 10 is located. Each one will be having its own dedicated address. So with the help of that address, your PLC is able to recognize each of its things located adjacent to the PLC. For example, location where the switch is physically connected to PLC. Each IO, each input and output also it can recognize. So now we'll try to draw some of the applications with the help of these symbols that is known as a ladder diagram. So these are some more symbols I have written here with some how to have some specific ladder diagram here. Ladder symbols you can see here. Input as contacts not closed until input. So this one is the contact that is not closed until we'll tell it. Until input. Until input will arrive, it will not be closed. So this is exactly reverse of this one. Input as contacts which are closed until input. Means as long as input is there, it is closed. Sorry. Until and unless you apply the input, it is closed. When you apply the input, it is open. When you apply the input, this is closed. When you apply the input, it is opened. Means till that it was closed. And this one till that it is open. Initially it is opened. When you apply the input, it is closed. Initially it is closed. When you apply the input, it is open. That's all. This is the output, which is the symbol we are going to use in the ladder circuitry. And this is the special instruction block we are using in the ladder diagram. Okay. Now you can see. So input 1, 1, we are going to indicate it here. Okay, ladder diagram with these symbols. Input 1, which will indicate that only when you apply the input, it will be closed. And output A, you can say, occurs when input 1 occurs. Okay. So now we can see output B occurs when input 1 and 3 occur. Okay. So it is something like an AND gate. We can see this one. So only when both you can apply, sorry, not, okay, AND gate. Only when both are on, you will be getting output. And output C you can see occurs when input 4 or input 5 occurs. Okay. So this you can see, this is something like an OR gate. Either this path you can reach C or this path you can reach C. OR is there. So this is the AND, input 1 and 3. This is the AND. This is OR. This is something like whatever input you will get, output is going to follow the input. That's all. This is follower, this is AND, this is how we are going to represent our basic gates with the help of this ladder diagram using ladder symbols. So this we can call end of program. This is, you can see, no, this block you are using special instruction, that is the end of program. So this is the ladder diagram that is normally used in PLC domain. Next, we'll see some of the examples here. Okay, switch controlling a solenoid. So you have here, we have got one PLC here, one black box is there, it written PLC, plus 24 volt and X400. So this is the switch from which we are getting the input. Okay, and output is here, that is a solenoid. So this one we have to write its equivalent ladder diagram. Okay, so the contact what we are using, X400 is the contact that we are using here to represent it as input. Okay, so only when you apply the input, this will be closed and input is applied to the PLC, and output we are getting at the Y430. Means only when you apply the input at X400, we are getting the output at Y430. That's all, and this you never forget to write the end. So this is a simple ladder diagram example to write equivalent to this figure here. So what this figure A is doing, output from PLC is to energize a solenoid. So output of this PLC is going to energize this solenoid, means it is controlling the solenoid when normally open start switch. Normally open start switch. Normally open start switch, when you apply the input, then it will be closed. Till that it is opened. That's what is known as normally open. Normally open means before applying the input, it is normally open. Start switch means when you apply the input, it will be closed. Then it is started. Connect to the input is activated by being closed. So when you apply the input, it will be closed. So this might be a solenoid valve which opens to allow water to enter a vessel. Means with the help of PLC, we are controlling the solenoidal valve that is controlling the water input and output into the or from the vessel with the help of this PLC. So this is how guys you need to explain each of these examples for the PLC relays using ladder diagram. First part, you have to explain how you are going to draw the ladder diagram with the help of the for the corresponding application. Then next, you have to elaborate its normal operation of the PLC using this ladder diagram. So another very good example is this temperature control system. Again, the same PLC block will be there with plus 24 volt. Input we can see we are getting here with the help of some rectangular box that is reserved for some instruction here. With the help of some instruction, it is coming as input and reaching at X400. And the output of PLC is going out from Y430, and it is going to control the another relay to which the heating element is connected, where we are going to have the control, temperature control. So this can be coupled with the help of the relay here. This will indicate it as a relay symbol. So let us see how the things are going here. So these four what the rectangular boxes what you are observing, adjust for set value means it is indicating four values are indicating four arms of your bridge. So one of the arm you can see it is a temperature sensor or a thermistor. Okay. So this one is going to sense the temperature. This one is going to sense the temperature. And according to the variation in the temperature, the bridge got imbalanced, and whatever the two inputs we are applying to the triangular structure, that is op-amp, differential thing we are getting here as output of this op-amp. And with the help of instruction that can be compared with this temperature variation, then it will be fed back to reconnect it. Then it will be arriving with the help of this instruction at the input X400. So you can see it is written here. The input goes from low to high when the temperature sensor reaches the set temperature. Set value is given here. Until this one we can vary. Beyond that it cannot be allowed to increase. The output is then go from on to off. So when the temperature is sensed, we are going to couple it to the relay here and it will be displayed. Then output will go to low, on to off. So you can see here, when the moment you will apply the input, temperature is sensed, this will be open circuited. Till that it is closed. Till that it is closed. The moment when you get the temperature sensing from the thermistor, this contact will be opened and it will be processed as per the set value, adjust for the set value. Then it will be given in hand to the output Y430. So this is how the temperature control system is going to operate. So this is how you are going to represent with the help of the ladder diagram. Again, don't forget to put the end instruction. Next one, logic functions. Example of logic functions. So just now I have summarized in the previous some of the slides how to represent AND gate. This one is for the AND gate ladder diagram with the help of such kind of contacts and the ladder diagram. Such kind of contacts and equivalent ladder diagram. If you get in series the contacts, it is AND gate or AND circuit. And if you get such contacts parallelly, it is called as a OR circuitry. So the logic functions can be obtained in the similar way by combination of the switches like this one. The figure shows how ladder programs can be written for such kind of combinations. You can use this as an AND gate, this as OR gate. You can use them as a basic gate in the design of any kind of a combinational or sequential circuits. So another good example, the enhanced one, the switches which are used for controlling a solenoid. Okay. So consider a situation where a normally open switch A, so this switch is normally open. It will be closed only when you apply the input. That is a meaning. Normally open means the switch is opened normally, generally. When you apply the input, it will be closed. Must be activated and either of the two other, that is B and C, normally open switches B and C must be activated for a coil to be energized. So A is always open. You can see here. So when we are getting the output, it is something like A ANDed with B or with C. It is something like this. If you look at this truth table, A is ORed with the AND operation between B and C. So B and C operation between them is only B and C is A AND gate. Sorry, A AND with B or C. Sorry, operation between B and C is OR. That is ANDed with A. B or C, 0 or 0 or 0. 0 AND with 0 is 0. That is correct. 0 or with 1 is 1. But this one output of A AND with A, that is 0, is 0. Again, G1 or with 0, 1, that is ANDed with A, that is 0. 1 or with 1 is 1, ANDed with 0, again 0. 0 or with 0 is 0, ANDed with A, that is 1, again 0. 0 or with 1 is 1, 1 ANDed with 1 is 1. Again here 1 ANDed with 1 is 1, 1 ANDed with 1 is 1. Means the whole equation data flow you can see as you are learning in the HDL, A ANDed with bracket B or C. That how we are going to represent it with the help of this ladder diagram. We are going to use three switches in the form of one AND and one OR gate, which are overlapped like this, and output we are going to get in this one. Solenoid is now indicated by this kind of ladder symbol. So this is how we have the switching controlling of a solenoid with the help of the help of the switches arranged in the form of the combination circuits. Next one you can say very popular example, the shop door system. Okay. So again we have here the PLC. Output is there here. Output and inputs are there here. Shop open customer. Output is there here. PLC output. Okay. So inputs are there. Two inputs are there. There are how many inputs? Two inputs are there. One is a shop open, another one is a customer approaching. So customer will approach when the shop is open. That is the correct condition. Then only will get the customer will get the some item. Okay, from the shop. So customer come and shop is off. No, customer won't get anything from the shop. Customer is not coming, shop is not opened, means it is nothing. No. So customer is not coming, shop is open means nobody is there, customers are not there. So customer is not getting no selling. So this problem, the shop door problem or system, how we can represent it with the help of the ladder diagram. So two inputs are there. So only when both are on, it should be on means it should be AND condition. Input 1 ANDed with input 2. Shop open and customer should be there. Both should be there only when then only will get the customer will get the item from the shop, like that. So like that you try to elaborate with the help of the truth table also, then the diagram. First you have to tell how we are getting the ladder diagram. The solenoid is represented by the circle and both the inputs are represented by the two contacts, and these two contacts are kept in series connection, not in parallel, because by looking at the truth table our customer is going to get the any goods from the shop only when the shop is open and customer is there, not in either of the condition. That's why it is like similar to the AND condition. So only when both conditions are satisfied, so our customer is going to get the goods from the shop. So they are resembling AND gate operation. So that's why both the contacts or inputs will be arranged serially to represent this AND gate operation or AND present condition. So output is represented by the solenoid like this. So next one, the example will continue here. Another thing that you need to remember, the two words here, the ladder circuitry. The vertical lines are known as bars, and horizontal lines are known as rungs. Vertical lines are known as bars, and horizontal lines are known as rungs, RUNGs. So ladder circuit consists of individual rungs. Okay, this ladder circuit consists of individual rungs. You can see horizontal lines. Rungs means horizontal lines. So each rung or horizontal line contains one or more inputs or outputs. It may be having one input or more than one input or outputs. So first instruction on rung must be an input instruction, and last instruction on rung should be an output coil. So you can see here. So both the switches will be acting like input. They are coming under input part, and the output we can see the coil here. In the coil solenoid we are going to control, that is the output. So this one we are going to end here with the end instruction. So we are going to, these horizontal lines are known, that's why he has told each rung contains one or more inputs or output. So we can see here, so this rung or horizontal line has got two inputs and one output. This is what we mean by one rung or is horizontal line. And finally we are going to wind up this ladder diagram with another rung containing the instruction end. So resistors used in indicating changing of switches like SW1 and SW2. So I already told each switch or whatever in PLC is having its own dedicated address. So PLC is a programmable one. It is going to control its on and off of anything on the PLC with the help of the respective addresses or coding. So with the help of programming or coding, it is going to control the switch on and off like that. That's all. We are not going to manually going to operate them. So you can see here two inputs are written with the addresses and output is having its own another address. And it is also having its own numeric address. So register 00 now it will be represented like this and 05 it will be represented like this. So with the help of this such kind of arrangement of registers which are used to hold these addresses and with the help of programming we are going to control the switches or inputs and the output solenoids like this one. So like that, one of the question that I asked in the assignment is like this one only. You need to explain that shop door or something I have asked you. So hope this point is clear, guys. So let me stop here to continue with what if you have anything to be discussed later.